Imagine the universe as a vast cosmic ocean. For centuries we've studied it by capturing light, visible, radio, X-rays, revealing stars, galaxies, and the afterglow of the Big Bang. But light is only part of the story. It's like watching the ocean's surface, never feeling its currents. Now we can sense the universe's ripples, gravitational waves. These aren't light or electromagnetic radiation. They're disturbances in space-time itself, like ripples from a stone dropped in a pond. The most violent cosmic events, colliding black holes, exploding stars, send out these ripples, traveling at light speed across the universe. Gravitational waves pass through matter almost untouched, carrying secrets from events hidden from traditional telescopes. They're echoes of ancient cosmic collisions, finally reaching us. For humanity, this is a monumental shift, as if we've gained a new sense, able to hear the universe for the first time. We can now listen to the cosmic symphony, the rhythmic dance of neutron stars, the thunderous crash of merging black holes. This new sense lets us probe the universe's most extreme environments and explore its hidden dark side. It's a new chapter in our journey of cosmic exploration. Gravitational waves are the universe's purest, most unfiltered messages. They allow us to witness gravity's power in its rawest form. We're no longer just observers, we're participants in the universe's story. The cosmos is no longer silent, it's alive with sound, and we're finally listening. In 1915, Einstein's general theory of relativity revolutionized our understanding of gravity, showing that space and time are woven into a single dynamic fabric, spacetime. Massive objects curve this fabric, and gravity is the effect of that curvature. Within this theory, Einstein predicted that accelerating massive objects would create ripples, gravitational waves. He doubted we'd ever detect them. The effects seemed impossibly small. For decades, gravitational waves remained a theoretical curiosity. Physicists searched for them, pushing technology to its limits. Then, on September 14, 2015, two giant detectors in the US registered a faint, fleeting signal, a tiny chirp. After months of analysis, scientists confirmed they had detected gravitational waves for the first time. The signal, GW150914, was the echo of two black holes merging 1.3 billion light-years away. Einstein's final prediction was finally heard. This discovery opened a new window onto the universe. It was a triumph of science and human ingenuity. The universe had spoken, and we were ready to listen. Detecting gravitational waves is one of science's greatest technical feats. The signals are unimaginably small. By the time they reach us, they stretch and squeeze objects by less than a fraction of an atomic nucleus. To measure this, scientists built LIGO in the US and Virgo in Italy, giant L-shaped detectors with 4-kilometer arms. Powerful lasers travel down these arms, bouncing off mirrors and returning to the starting point. Normally, the beams cancel each other out, but a passing gravitational wave distorts the arms, letting a tiny flicker of light reach the detector. This flicker is the sound of space-time ringing. Earth is noisy. Earthquakes, trucks, even distant waves can disturb the detectors. That's why there are multiple detectors, thousands of kilometers apart. A real cosmic signal appears in both, almost simultaneously. Local noise does not. Sophisticated isolation systems help filter out Earth's noise. Only then can scientists listen for the faint whispers from the cosmos. It's a triumph of precision and perseverance, and it's how we hear the universe's most dramatic events. Detecting a gravitational wave is just the beginning. The signal is a wiggle on a graph, a mystery to decode. Scientists use mathematical models based on Einstein's equations to predict what signals from different cosmic events should look like. These models are like a library of cosmic fingerprints, each one unique to a specific event, like two black holes merging. When a signal is detected, it's compared to this library to find the best match. This reveals the properties of the event, the masses, spins, and distance of the black holes. Creating these models is a massive challenge, requiring supercomputers to simulate extreme gravity. The result is a vast catalog of possible signals. Matching the observed signal to a model unlocks the story hidden in the data. It's how we turn a fleeting ripple in space-time into knowledge about the universe. Without these models, the signals would remain an untranslatable language from the stars. How do scientists match a noisy signal to the right model? They use Bayesian Inference, a powerful statistical method. It's like making an educated guess, checking it against new evidence, and refining it until it fits. In gravitational wave astronomy, scientists start with a prior, a range of possible properties for the black holes. The algorithm compares millions of models to the data, scoring each by how well it matches. With each comparison, it refines its estimate, zeroing in on the best fit. The result isn't a single answer but a probability distribution, showing for example a 90% chance the black hole's mass is between 35 and 40 times the Sun. Bayesian inference gives not just an answer but a measure of confidence. It's the most honest way to extract knowledge from noisy data. This method powers our ability to interpret the universe's faintest signals. It's how we turn cosmic whispers into scientific discovery. Our understanding of gravitational waves depends on the accuracy of our models. But what if the models are flawed? Even small inaccuracies can lead to big errors, misjudging a black hole's mass or spin, or misinterpreting a signal as new physics. These aren't trivial mistakes, they affect our answers to the universe's biggest questions. Our models are powerful, but they're still approximations, limited by the complexity of the simulations. Until recently, scientists had to assume their models were perfect, because there was no way to account for their flaws. This is a fundamental problem. To trust our conclusions, we must account for imperfections in our maps. The quest for precision demands a better way. Enter Dr. Christopher Hoy and his team at the University of Portsmouth. They recognized the problem of imperfect models and developed a groundbreaking solution. Their new statistical technique lets scientists include model uncertainty directly in the analysis. Now, Bayesian algorithms know the models might not be perfect. By comparing different simulations, quick and rough versus slow and detailed, they measure the uncertainty in each model. This information is fed into the analysis, making it more flexible and honest. It's like a chef adjusting a recipe, knowing the spice amounts are just estimates. The result, more robust, reliable scientific conclusions. Instead of forcing data to fit a rigid template, the method allows for a nuanced conversation between theory and observation. We get more accurate estimates of black hole properties and a realistic measure of our uncertainty. It's a huge step forward for precision cosmology. Now we can trust what gravitational waves are telling us. Dr. Hoy's method is like improving a police sketch. The old way took every detail as absolute fact, creating a sharp but possibly wrong portrait. If the witness's memory was fuzzy, the sketch could be confidently inaccurate. The new method acknowledges uncertainty, producing a softer, more honest image. The result might look less certain, but it's far more likely to be accurate. This approach refines our cosmic measurements, widening error bars but increasing confidence that the true value lies within. It prevents us from chasing ghosts, mistaking model errors for new physics. We get a clearer, more reliable picture of the cosmos. The universe's portrait is no longer a blurry sketch but a beautiful, accurate image. We're finally seeing reality as it is. This breakthrough transforms gravitational wave astronomy. By accounting for model uncertainties, we sharpen our tools for exploring the universe's greatest mysteries. It's essential for testing Einstein's theory, ensuring any deviation we find is real, not a model error. More accurate measurements reveal how black holes are born, grow, and shape the cosmos. Each improvement brings us closer to answering the biggest questions. Where did we come from? What is the universe made of? What is its fate? Gravitational waves are a new language, and we're learning to read the universe's epic stories. With every discovery, we unlock more of the cosmos's secrets. We are at the dawn of a new era, listening to the echoes of creation, and finally understanding the universe.